Evet. Alright, so what did we do? So, okay. Which one did I erase? Okay. Right, so we know that this is correct, right? Because now bits have exponential distribution, right? So we can just keep that and erase the rest, right? And quickly, let me just complete this and then we'll move to a new topic anyway. And I was interested in calculating what? So we would like to know how much we are going to earn when we actually sell the asset, and we said from the first part we know that this is the same as the conditional expected value of one of the bits given that x1 is greater than a, right? And then now actually I just did that experiment, exercise, right? So we can just write x as a plus the excess over a, right? A plus excess over a, condition on x1 on the event that bit is greater than a, right? It is again the conditional expectation of sum of two random variables, one of which is deterministic, so its expectation is itself, in fact, and therefore you have conditional expectation of a, which is itself, plus the conditional expectation of x1 minus a given x1 greater than a. Okay? Now that's what we want to calculate. But from this, right? Okay, now let us rewrite this in terms of a. So if this is true for every x and y, for every positive x and y, then it is also true. Okay, let me write it a little to the right. So this is also true for the probability that x1 is greater than a plus some y, conditioned on, right? x1 is greater than a, right? Just like here, you condition on the event that x1 is greater than a. And because of the memorylessness property, this is the same as what? Unconditional probability that x1 is greater than y. Because all of a sudden, x1 forgets about its age, right? It is actually at least as old as much as 8 years old, but he doesn't remember that. And now we can rewrite this one, right? So you can just take a to the left-hand side. So this is the same as the probability of the event that x1 minus a, right? The excess is greater than y given that x1 is itself greater than a, right? So you look at this, right? What is this? Let me write it in a nicer way, like this, right? So this is like what? The conditional distribution of this random variable, x1 minus a, given this event, is the same as unconditional distribution of x1, right? The same y appears on the same in the same places, right? Right? Namely, right? Given that x1 is already greater than a, the random variable, right, x1 minus a, has, right, conditionally the same distribution as the unconditional distribution of x1, which happens to be what? Exponential, right? Exponential. So therefore, I don't have to formulate this statement in terms of x1 itself. We could just write directly what it is, right? So x1 minus a has conditionally exponential distribution. With rate, of course, lambda. It doesn't change, right? So that's very important and very useful. Well, if conditional expectation of x1 minus a given x1 is greater than a has exponential distribution, then its conditional expectation, right, given the same information, is the same as what? The mean of an exponential distribution with rate lambda. And what is that? It is just 1 over lambda, right? So therefore the answer is A plus 1 over lambda. Okay? Right? Any questions about that? All right? And that concludes the discussion of this one. And then, if you don't have questions, this just completes the review of conditional probability. Right? Right? Now, we'll meet next Markov chains. Right? So that's the next topic. So that's the real stuff, in fact. So Markov chains are ubiquitous. Actually, they have been used in many areas. One reason is actually they actually give a natural, very intuitive way of embedding forgetfulness properties. So when you observe many things around you, you know that there are actually very complicated interdependencies between things that happen over time, and doing any calculations while you are actually keeping all these interdependencies is almost impossible. You cannot really work anything tractable out of that. The Markov processes, what is really typical of these guys are, if you give enough information, the future events turn out to be independent of what happened in the past. So you don't always remember the entire history coming from the past. Somehow, if a process truly has Markov property, which is equivalent to saying that it has some kind of a memorylessness property, just the exponential distribution itself, then you don't have to remember everything from the past. You keep a sizable information for today in order to make predictions for future. When tomorrow comes, you can forget what happened in the past. You just keep what you have just learned, use that to further make predictions for future. And it's a dynamic system. It goes like this forward, right? And there are, for example, DNA sequences that people are trying to match them with whatever functions the proteins produced by those DNAs, whatever those DNAs are responsible for, are being, for example, modeled by Markov chains. They use Markov chains, and they don't know what one-step transition probability is. They, in fact, conduct a lot of experiments, observe how things actually convert from one element to another, and somehow estimate those probabilities. And that's one way, for example, one tool that the biologists use to understand how the DNAs work. It's a quite recent work, so people are still actually in the process of identifying the gene map, for example, in a human being. I don't know whether it's still it has been completed, but probably not. Well, there are other examples as well. So, being an industrial engineer, you will see that actually in production systems, in queuing systems, processes, the number of customers arriving, customers leaving the system, they are conveniently modeled by Markov chains. We will see that they actually show up in a very natural way as well. Okay, so we'll see a couple of more examples, and then we'll work out the details along the way. So, but let me first define what a Markov chain is. Right? What is Markov? Markov is the name of a mathematician. I don't remember right now. I'm very bad with the names, so I don't remember even the first name. And actually, he was originally interested in formulating Markov chains when he was kind of trying to find a signature of a very famous Russian writer. So what he was thinking like, well, a writer must have a typical style, right? Orhan Pamuk has one, Orhan Kemal has another. So somehow there must be a way when you, if nobody tells you who wrote a book, right? You get the book, you read. If you have kind of a knowledge, if you have already read books from various writers, you might be able to tell actually who wrote that book, right? So humans have that ability. But we don't still know how exactly that our brains work and pick up, for example, okay, this style doesn't like Orhan Pamuk's way. This must have been written actually by Orhan Kemal, for example, right? So a similar, so Markov was trying to mathematically formulate that problem, right? So how can you model a book? It's the sentences, right? When I was in Ankara, right, you write a novel like this, right? So after when I follows, after I was comes, Ankara was followed by this and that. And okay, this is not the best example I can give, but the idea is to see these words like actually a realization of a Markov process. Okay? These are the states coming from the state space. You have a random process xn. At time 0, it happens to take this state and then moves to state x1, I, moves to state x2, right? A Markov's process is characterized what we call the one-step transition probability. What it says that whenever you see Ankara, the next word it is going to follow is going to be Izmir, Istanbul, or maybe something else, right? You have the entire vocabulary of a writer with such and such probabilities. And those exact probabilities are kind of a way how the style of a writer actually forms. That's what the Markov was thinking at that time, right? So some people use several words right after the others repetitively. It's just a style, right? Right? I don't know a good example of thing. I don't know. Maybe I probably repeat myself. For example, I say the right. Too many rights coming. My wife was warning me that I shouldn't use that too much. But see, that's like it just builds into your system after you teach so many times. If it is too late for somebody else to warn you, it just lives with you. That's like a start, right? So if somebody says, okay, in the class today we heard a lot of rights one after another, you can then say, with probability 1, the one-step transition probability for this professor must be like, after right, the next word is going to be right with probability 1, or with a high probability. That probability transition matrix is most likely to belong to Professor Dayanık. There you can immediately identify. Now, it cannot be Sabucioğlu, it must be Professor Dayanık, right? So something like that. Markov was working on something like this. I guess, I don't remember the writer, maybe Pushkin. He pulled his books and I count the frequencies. After this word is coming. The pair of the words coming one after another. He built up a one-step transition matrix. And he used it to kind of predict what the next word is going to be. Right? It might sound like a silly work, huh? But actually after so many years, people are now using it to identify the authors of works that are not known, whose authors are not known. For example, still there is Homer, right? The Iliad, Odyssey. It is people still not quite clear. I'm not certain whether they were really written by Homer or somebody else. And then they are just studying around. There are a couple of infamous books like this as well. In the United States, for example, during the Revolution, I guess, people used to write articles in the journals, and there was a revolutionary group of people, and they were just signing the revolutionists, for example. It was not known, it is not quite clear actually who exactly, which person inside the group wrote those things. Now, people are interested in who wrote them. And they are now collecting works, different things that they know were signed by each of these people. They create a model, the Markov process, Markov chain. They basically derive the one-step transition matrix. And when a new work comes, whose author is not known, they compare with different one-step transition probabilities in order to identify the author. Now today is even a lot more popular because there is this terrorist trying to attack us or attack the United States, whatever. Right? So then now trying to see, well, if you see this piece of email, for example, emitted from one place to another, is this being written by a person, a dangerous person that you met before or not? So these are known as like identifying the author of a document. So the Markov initiated this for one reason. It has been used for many other purposes, but apparently actually now a lot of people outside are interested for the very same reason why they were originally discovered. Well, we'll see other applications as well, which are probably also important for for your career, right? So we'll see a couple of queuing models as well as inventory models, among other interesting stuff as well. So I haven't defined it yet, right? So let me just do that now. So this is like what? A sequence of random variables, right? Taking values from the same set E is called a Markov chain with state space E. If given the state at some time, future states are independent of the past. Okay, this is too long. Let me write it. So we say that a sequence, right? So I'll denote it by X, but this is a sequence of random variables. Okay, from 0 to infinity, if you like, right? Of random variables. So each one of them is a random variable. Right? So they are all defined on the same probability space, right? Okay. Taking values in the same set E, right, is called a Markov chain, right, with state space E, right? So that's what we are trying to define, right? If, right? So given the state xn of the chain at time n, right? Okay, the future, how do you define a future for a stochastic process? Well, it is anything that you will show, anything you will see after time n, namely x. The state at time n plus 1, denoted by xn plus 1, xn plus 2, the state at time n plus 2, and so on and so forth, right? It's the future of this process, right? The future, right? Okay, maybe I should say that I like the most. So let me just squeeze it here. The future states, right, given by this, right, are conditionally, too many words, important words, they are conditionally independent What are you conditioning on? The state given at time, right? So given that piece of information, future states are now conditionally independent of the past states. Now what are they? This is the x0 state at time 0, x1 the state x at time 2, and finally xn minus 1, the state just before time n, right? Okay, that is the defining property of a Markov chain. So there are plenty of sequence of random variables outside. Not all of them are Markov. Which ones are Markov? The ones that have this forgetfulness property. Is there a forgetfulness property here? Yes. It forgets about past. Under what conditions? If you know the state today, right? Time n is like today. If you tell what the temperature today outside, you don't need to remember what the temperature outside was tomorrow, 2 days from today, 2 days before today, 2 days or 3 days before today, in order to predict what the temperature is going to be in the future, right? So that is going to be true if temperatures over time really follow a Markov chain. So that's a debate, of course. If somebody says it is Markov, then you should expect the process to have this property. All right? So for simplicity, we will assume that state space E, right, is countable, which means nothing more than that you can enumerate all the states with integers. Okay, can be enumerated with integers. Okay, that's just to make the life easier for us, otherwise, right? And this property that I just wrote, right, I said belongs only to Markov chains, is also known as Markov property. A sequence which has this property is said to have Markov property, okay? And we can actually formulate it in a concrete way, right? The Markov property can be, okay, written as, right, so obviously this statement contains some conditional probabilities, right? So it is then not surprising to write, well, what is the probability that at time n plus 1, the state of the chain, or the chain, this process is going to be in state j, right? So, okay, I am going to write it in a moment. Given that at time 0, let's say the process in state, some state I0, at time 1 it is in some state I1, and finally at time, okay, let me stop at time n, it is in state, in some state, do I want to do that? No, I'm not going to specialize on that. Let me just also include state at time n minus 1, okay, n minus 1, and at time n, let's say it is in state I. Okay? See, this is only the difficult problem. So you collect, so for each different values, you are supposed to estimate those probabilities. If you ask a statistician, he's going to just, actually, we'll say, well, forget it, right? So for each possible values here, so there are n plus 1 and plus 2 values. It is really difficult to get these numbers from outside, unless the process has Markov property. And that means that this really doesn't depend on any one of these numbers, it only depends on I and j. And that's exactly the Markov property. If this can be written as the conditional probability of the same event given only the most recent observation at time, then you are in business. Okay? And this is a Markov process, therefore life is going to be easy. So of course, you have to check this for every integer n, first of all. Okay? And for every possible combination of states I0, I1, and so on, coming from your state space. All right? In a moment, I'm going to give an example. Maybe this is too abstract, too difficult to visualize. But while we are at this, let me also introduce a couple of things. Okay? So is this really this statement here? It is. So this is the future, because this is the present. Okay? And this is, therefore, the past. Right? So the future state of Markov chain is independent of the past, because right-hand side doesn't really depend on any one of these values. You know or you don't, right? The result doesn't change on the right side, given the present state, right? So it is exactly this statement, right? And this right-hand side, which depends on the I and j, right? Sometimes people denote it by Pij, right? Is called one-step transition probability. And you may actually notice that there is this quantity may also depend on n, which I didn't really take into account on the right-hand side. That's because in this class we will be working with time homogeneous Markov chains. which means that one-step transition matrix and the one-step transition probabilities are all the same at every time. All right? What if it is not the same? Well, there is a simple way to convert the time inhomogeneous Markov chain, namely for which the one-step transition probabilities also depend on n. There is a way to convert such things to time homogeneous Markov chains for which this really is not there. Right? I might just assign a homework for this. It's a simple transformation. So I'm not going to spend time in class for that. I'll just go forward and we will assume that probability of moving in one step from state I to state j is always the same at every time n. Okay? That's what we are going to assume. Right? And this is once the transition probability, and you can actually, so you have what? For each I and j, you have one such number. But if you have such numbers, you can actually, countably many such numbers, you can actually arrange them into the form of a matrix, right? And define a matrix P, right? A matrix looks like an array of this kind. So there will be, so we said states can be enumerated with integers like this, right? 0, 1, 2. So there are rows and there are columns, right? There will be ith row and there will be jth column. And this Pij, ij of this matrix is going to be just this number. If you just take these numbers and populate a matrix like this, you then get the so-called one-step transition matrix, transition probability matrix. Okay? These are convenient objects that we can use to write things compactly later in this class. Right? And if you look at this thing, right, if you fix I and look at the ith row, you'll look at the numbers on the ith row, right? So you just collect Pij's, right? You fix I, then you look at Pij's as j changes, right? Right? These numbers. What do you see here? First of all, you know that each of these Pij is between 0 and 1. It is between 0 and 1 because they are probabilities. They are conditional probabilities. They are supposed to be between 0 and 1, right? Because 1.2 doesn't make sense, right? As a probability. Okay, what else? If you sum Pij over j, all possible values that j can take, it is going to be 1, right? Why? Because, well, this is like the probability that tomorrow you will be in state j, given that today you are in state I, and you sum all these probabilities over all possible j's, places that you can be in tomorrow, right? Well, if you sum all these probabilities over all possible places you can be tomorrow, right? There is no other way that you can escape, right? So it is 1. It should be 1. So namely, this is itself like a probability mass function. All right? That's an important, useful observation. All right? And why do I emphasize so much about one-step transition matrix or one-step transition probability? The reason is, if a process indeed has Markov property, you only need to know the one-step transition probabilities in order to calculate any kind of probabilities that you want to know. All right? If you also know the initial state distribution, I must say, and let's see that. Let's just see how you can do those calculations if you have one-step transition probability matrix and initial state transition probabilities. So I would just say like the finite, so this is the formal name for that, finite dimensional distributions. Okay, let me write it. Dimensional distribution of a Markov chain. So I am going to use MC. I am going to write MC rather than Markov chain all the time. So that's the acronym that I will use standing for Markov chain. Alright? Right? Okay, finite dimensional distribution of a Markov chain is completely determined by two things. One is the initial state distribution, and this is nothing but the unconditional probability that at time 0 the state of chain is I for every possible I. So that's called the so-called initial, because at time 0, so that's when time starts, when the process starts evolving forward, right? According to our clock. And also, well, one-step transition matrix, or the probabilities. One-step transition probability matrix P. Okay? Why is this true? Well, by finite dimensional distribution, what I really mean is this. So for example, you want to calculate the joint probability that at time 0 the chain is in I0, at time 1 it is in state I1, and finally at time n, for some finite n, the chain is going to be in state In. It is finite dimensional. There are n plus 1 possibilities that you are trying to figure out what the probability is going to be, right? But it is arbitrary in the sense that you should be able to find out what these probabilities are for any given n, and any choice of states I0 to In. And now, how can I write this in terms of this too, if that is really true, right? Well, we will use this recursively the conditional, the so-called the tower property of conditional expectations. The name is fancy, but it is nothing but it is just Bayes' theorem. And also the Markov property. So what is this? We can just condition on the first states of the Markov chain up to and including time n-1, right? Like this. Okay, I don't break this sequence of expressions until this, and then close it, and condition on this one. The times the condition for the xn plus at time n plus 1, the state of the chain is In plus 1, given all this information. Okay. Can I do that? I couldn't do that because of the definition of this guy, right? So this is like event B for me, this is like event A, and this is probability B given A. But then this is probability of A, right? Probability A times probability B given A is, of course, probability of A and B. A and B means what? This is A and B. It is exactly this, right? So having a bunch of details doesn't really change what the theorem stands for. Why did I do that? Why did I do that? Well, here I can use Markov property. So this is future for me. This is, what happened here? It is wishful thinking. It is only n, right? So I have this, in fact, right? So in this case, this is like future if n-1 stands for the present, right? So I know the chain, the state of the chain today, trying to make an inference about the state of the chain tomorrow, right? Also, I am given the more information about where this chain was in the past. But the Markov property says to me that if you know the state today, to make an inference about the future, you don't really need to remember what happened in the past. This is because future is independent of the past, given today, right? So now, this part just simplifies, so I have the probability that x0 equals probability of all these things, right? This is almost the same as this, except that there is one less. So my problem size just decreased. And what is this? Let us write it here instead. So this is the conditional property that at time n this changes in state in, given that at time n minus 1 it is in state in minus 1. Which is what? If I use the same notation from n to n plus 1, we said we are in time homogeneous. So in one step going from I to j is denoted by this probability ij entry of this matrix. Then this is right going in one step, right, and from n minus 1 to n, from state in minus 1 to in one step is given, right. The probability of this transition is given by the in minus 1 in entry of one step transition matrix. You look at that, right, and then you finish, right. So then you know, okay. So we know what this is. We will just write it here. Without a bar, it is P of in minus 1 in, right? So I started with in. Now I have a similar quantity, but only up to in minus 1 less, times a quantity that I know, right? But then you can apply the same argument to this one. So you condition on the information up to information about the states up to n time n minus 2, you repeat it, then you will get, where should I write this? Let me just write this and then finish today's lecture. You will just take that, and it is gonna take the following form. If you repeat this n times, you will end up with this alone times the probability of going from I0 to I1 in one step, which is given as by the I0, I1 entry of one step transition probability matrix. Then from I1 you go to I2 with probability given by the I1, I2 entry of one step transition matrix. Now you see how this goes like this. And finally you are supposed to go from state in minus 1 to state in, whose probability now is given by the in minus 1 in entry of one step transition matrix P. The same. And this is what? This is nothing but the initial state distribution. So when you have these two pieces of information, initial state transition probability, and initial state distribution, and one step transition probability, then you can figure out probabilities of this kind. Thanks to Markov property, right? I use the Markov property. Where did I use that? Here I use Markov property to cancel out anything related to the past, right? So only the present and the future were relevant. That's where I use Markov property. And I used Markov property how many times? N times, in order to get each of these things, right? So therefore we like Markov property. It forgets about the past if you just give present. And we'll see that that will make, as I claimed at the beginning of this lecture, it will simplify a lot of calculations, probability calculations, right? So let me just stop here, and then I'll continue this discussion on when? On Friday, right?
Thursday or Friday?
Yes. I'm too fast. Forget about Friday, Thursday, first at 13:40, am I right? It's a good thing that I wrote it, because otherwise, so I was just traveling too much, I guess. I already forget that I should be here on Thursdays as well. Okay, I'll see you on Thursday.